integration of functions of more than more than one variable, although we're chiefly going to look at functions of two variables for the moment. And we introduced this last time. We made it clear there was going to be a couple of different types of integration. And the first ones we looked at were so-called line integrals, or path integrals, or integration along a curve, sometimes called. And this was where we took these expressions L here, the top of page 23, and these were linear differential forms. So a p dx plus a q dy, where both the p and the q themselves were functions of the two variables x and y. And these objects could be integrated along curves in the plane. Okay. And the technique for evaluating them that we looked at was working from the description of the curve. If you've got a formula describing the curve and you know the start point and the end points of the curve, this should be enough to translate the integral, which starts off as an object mentioning both of the variables x and y. You should have enough information from the specification of the curve to translate the whole thing into a more recognizable standard integral with respect to just a single variable. Okay? Now, without working through the details again, but this first example we looked at was along the curve y equals x squared. So this curve going from the origin up to the point 1, 1, specified by the formula y equals x squared. Well, that's enough. By just direct substitution, we can replace every y we see with the quantity x squared. And by applying the chain rule, we can replace the differential dy by 2 times x dx. So the differential dy gets replaced by a combination of x multiplied by the differential dx. And making those substitutions, we can translate the initial integral into a recognizable integral with respect to a function of a single variable between two limits. Something that is the bread and butter juice. Okay. So that was the initial idea of path integrals. We then looked at nice properties that they have. Just giving a quick recap. First of all, like integration of a single variable, this new integration of two variable functions is still a linear operator. So if you're applying it to linear combinations of things, you can still break that up into the appropriate linear combination of the individual integrals. And these properties all kind of mirror, they're all generalizations of similar properties for normal one variable integrals. The second property was that if you reverse the direction along the curve, so still integrating over the same curve in the plane, but now going in the opposite direction, what that does is that changes the sign of the integral, just as it did for the one variable case. And thirdly, we can split the curve up into a number of different, different parts. And say that the integration along the whole curve, so in this, when we explain this here, so you've got some curve A to C, and there's some intermediate point B. And this is saying that, well, the integral from A to C along that curve, we can first integrate from A to B as a separate integral, evaluate that, separately integrate from B onto C, evaluate that, and when you add the two together, that's the same as just integrating in one go along the curve. Okay. And this is useful because in certain problems that we look at, different parts of the curve are described differently. So the translation, where you translate the integral into just a single variable one, the translation can work differently on different parts of the curve. Okay? If your curve sometimes is a horizontal line, then there's a diagonal line, and then goes along some function curve, there's a horizontal line, then there's a vertical line. you wouldn't want to integrate this all in one fell swoop, because the description of what's going on the curve is quite different. So there's a very natural subdivision of a curve like this into a number of different subparts, and then you would hope, given the precise description of each subpart, you would hope to separately treat the integral just on that subpart, okay, and then add up the results. Okay. So that brings us on to the new section 1.14, where we're going to start to describe the second type of integral, which is called double integration. Double integrals. There's a bit of a picture there in the book, but I just want to present a more general diagram to begin with. So we've got our familiar picture of three-dimensional space with the Cartesian x, y, and z axes. If we have a function of two variables, x and y, then through this equation, taking the value of the function f evaluated at x and y, taking that to give you the height of points, then this function describes some kind of a surface lying in three dimensions above, well, I'll just say above the plane. First, it's literally above the xy plane in neighborhoods where the function is positive. In areas where the function is negative, the surface will be going beneath the plane, because those, when you're beneath the plane, when you've got negative z values. Now, this second type of integration, just in general, is going to allow us to take a somewhat arbitrary, or some kind of nicely described region in the plane. So we'll have R, which is a subregion of the xy plane, and it's going to allow us to look at the cylinder, if you like, not very good picture, but dotted lines there. Anyway. What we're going to be describing here is the volume of the cylindrical, that's not really what you'd call a cylinder, but it's the cylindrical subregion or subvolume of R3 with vertical sides, base R, the base of this cylinder type thing is this region R in the xy plane, and bounded at the other end by the image of R on the surface defined by the function f. So this is very much the generalization of the familiar one variable picture, where you've got a graph of a function y equals f of x. You've got some subregion of the plane of, sorry, not of the plane, but of the domain of the function, which is just the x-axis, just a line, just a copy of R. So some subregion of that is just an interval. And just as integration, where you integrate the function in some sense over the interval a to b, that gave us the area. The area in this shaded region between the subpart of the domain between a and b and the function on the one hand. Well, here we're just describing the analogous thing, but when you increase the dimension. So when your function f is now a function of two variables, x and y, the equivalent thing to the curve defined by y equals f of x is now the surface defined by z equals f of xy. Think of that as this kind of flexible rubber sheet above the ground floor plane, above for positive values of z at least. You've got some subpart of the domain which was an interval, a subinterval of the x-axis, but is now some nicely described subregion of the xy plane. Instead of looking at just the area, the two-dimensional area bounded by that at the bottom and its image, see its image up here is like f of a, this is the point with coordinates a, f of a, f of a, f of b. This is kind of, if you like, the image of the interval a to b on the function, on the graph of the function. Well, in the same way, up here, upstairs, we've got an image of this subregion R on the surface. The image under just projection straight upwards onto the surface. Okay? So there's a volume in there, in that cylindrical, in quotes, region, and that's what we want to describe. And this volume will be equal to, well, this is, we want a double integral. A double integral to describe it. This dx by dy is called the area element, sometimes written as dA. So rather than having a kind of arc length element or a length element of the one-dimensional curve here, we have an area element, dA. Now the area element dA in Cartesian coordinates, it's equal to dx dy. The area element dA is supposed to represent a little bit of area in the plane that you get by varying the coordinates. If you vary the coordinates, the Cartesian coordinates a little bit, sorry, it's extremely small. You vary the Cartesian coordinates a little bit, the resulting area is simply dx by dy. So when you vary x and y, you're describing a little rectangle. It is area dx times dy. But in other coordinate systems, and we'll get onto this in due course, in other coordinate systems, such as polar coordinates, the area element can look different. It'll be different combination of the differentials of the variables. Okay? But we'll get onto that in due course. We'll also be able to generalize this kind of integration further into 3 dimensions, into functions of 3 variables, where the domain of the function is the whole of R3 space. Then we'll be able to integrate over sub-volumes, subregions of R3, and that will give us some kind of a 4-dimensional volume. Okay, but this is the picture here. Okay, how are these integrals defined? Well, we're not going to go into it in terrific detail, but we'll mainly concentrate on the methods. Since this mathematical methods unit, we'll mainly concentrate on the methods used, the evaluation techniques used. But this can be defined rigorously. Using subdivisions of R. R is this region in the plane. So here's a little picture of R. And we can imagine splitting R up into lots of tiny rectangles. Subdivisions of R into many rectangles. We won't worry too much about this, but we'll just refer to lots of little rectangles, Ri, R1, R2, R3, R4, R5, R6, just a whole bunch of tiny rectangles approximating Ri. And we can kind of give a one-line kind of limiting definition that defines what the integral is. And if you use some subdivision of the region R, so there in that picture, I've split R up into loads of tiny rectangles. We could approximate the true cylindrical volume over R there by looking at all the little cylindrical rectangles. The rectangles with the cylinders with a rectangular cross-section, rather than this wavy, curvy R cross-section. The little cylinders with a rectangle cross-section bounded below by the bottom rectangle and bounded above, well, approximately by a rectangle at the height of the surface. So we can kind of say that the integral over R of f of x, y, dx so I want to build this up, but we're going to take the limit as the radius of the Ri's tends to 0. I'll just leave that loosely described like that. So we're letting the radius, or the kind of maximum radius of these rectangles, or maximum diameter, just letting the size of these rectangles shrink to nothing, taking the limit of this, and you're adding up over all the rectangles I, the area of Ri multiplied by f evaluated at xi, yi, where xi, yi is an element of the rectangle little I. R xi, yi is an element of the rectangle Ri. So inside each of all these rectangles, you can imagine these representative points, xi, yi. And we're taking the value of the function on that representative point to be the height of our cylinder. Remember, the height of one of these cylinder type things is the area of the cross section times its height. So that's what we got here: the area of the base rectangle times the height that we're using. Now, if the subdivision is good, if you've got your region R subdivided into like millions of little tiny rectangles, then these two things on either side, we can take this summation of the volumes of all these millions of skinny cylindrical little volumes. We can take that as a good approximation of the true integral, because your collection of rectangles will approximate R very well. Of course, at the edges, there'll be all these little gaps and overshoots where you're counting rectangles that overshoot the area somewhat, or maybe leave a little gap of the area R that isn't considered. But if you've got a very fine subdivision of R into rectangles, this summation will approximate the integral. And the idea for the rigorous construction is to take the limit of these as the maximum radius of the rectangles converges to 0. Because in the limit, you're capturing the true base area R. Okay, so that's what we're about. That's the basic idea. But we need to start to look about how we actually evaluate these things. So the simplest case first is where the region R is itself a rectangle. So not some wavy wobbly R like this, but just a simple rectangle in the base plane. So that's the idea pictured in figure 1.5. Just maybe reproduce this here. I'm going to add a little bit to this diagram here. So we've got some rectangle R there. Being a rectangle, it has two limits on the x-axis, two limits on the y-axis. Now it's slightly even simpler than a rectangle. It's rectangular regions aligned with the axes, meaning the two sides of the rectangle are parallel to the x and y axes. It's not just an arbitrary rectangle. There might be at some non-right angle to the coordinate axes. What's this nicely configured rectangle here? Well, above the rectangle, will be the image of R on the surface. So the volume we're going to be capturing is the volume in this rectangular cylindrical region where it's got a nice clean rectangle R at the bottom and then maybe some wavy non-rectangle at the top, because this is actually lying on the surface. And in this case, the double integral, the way we evaluate it, is as a repeated integral. So this double integral, the way we actually evaluate it is with a pair of nested integrals, where we're integrating the function f of xy with respect to x. Sorry, my limits a and b are on the bracket there as opposed to on the bracket as opposed to on the integral sign. The inner integral integrates with respect to the x variable, and that integrates from a up to b. And then the outer integral integrates from c to d. And the thing you're integrating is the value of the inner integral with respect to y. So what we need to imagine here is within this cylinder, you've got this kind of vertical sheet. This vertical sheet is located at some value on the y-axis. So that value y there is the location of this vertical sheet. So it's like a cross section, or it's like a slice of the cylindrical volume. And this integral here gives us the area cross section depicted here at level y. So when you integrate this cross-sectional area across the cylinder from the starting value of y at c That's when this cross-sectional sheet will be at the front of this diagram. You integrate it to the back all the way to the value d. The thing is you're summing up all the areas of these vertical sheets. And that idea of slicing a three-dimensional volume up into sheets, an infinite amount of sheets, and adding up all their areas, that gives you the volume of the three-dimensional space. So the whole process can be thought of as summing up, but in a continuous sense, so you're integrating, summing up the cross-sectional areas to give the required volume. Is that okay? I think the best thing to do now is to dive into an example, see an actual concrete example of one of these. But it's important it's very important to make these links between the kind of individual evaluation steps we're going to go through and what's going on in the geometrical picture. Okay, so we'll look at example 1.18, 18th example in chapter 1. So we're looking at integrate this function, f of x, y. So it's not too bad. It's a polynomial function. Plus 4x plus 3y plus 1. Integrate this over the rectangle with limits 0 and 2 on the x-axis and limits 1 and 3 on the y-axis. Now, it's a good idea just to, when you're doing these, just to get a kind of clear picture of where you are. So it's normally a good idea to maybe sketch out the xy plane. So I'm going from 0 to 2 along the x-axis and from 1 to 3 along the y-axis. So the rectangle I'm talking about is this one. We'll call that R. Okay, so this is the particular function I'm talking about. This is the particular rectangle, and it is nicely aligned with the coordinate axes. So we're doing now an example like that general one depicted here. So we're going to be taking the double integral over R of f of x, y, dy. And so using this idea that we just went through, this becomes the integral from 1 to 3 of the integral from 0 to 2 of f of x, y with respect to x. And that outer integral is with respect to y. Is that big enough for everybody to see? Okay. So now we perform these integrals. Okay. Inner integral first. Now remember, the value of doing the inner integral is the cross-sectional area of that vertical curtain through the cylinder located at the level y. So the value of this integral itself will be a function of y. For different values of y, different values of the variable y, this integral will give different values. It's very much like the reverse process to partial differentiation. So we're integrating with respect to x here. So everywhere we see the y variable, we just leave it alone, treat it as if it were a constant, And just carry that through with the integration with respect to x. So the outer integral remains unchanged. We're integrating the inner function with respect to x. So it has integral x squared y is 2x squared plus 3xy plus x. So you see what's happened there? We've integrated the polynomial with respect to x. So the other variable y is treated as if it were a constant. So it travels through still as a constant. So this 3y here, that's just like a constant. So you integrate it, it ends up multiplying x. This constant 1 multiplies x. The 2xy integrates to x squared times y, etc. And then you evaluate it at the limits of integration on the x variable. Well, one of the limits is 0. That's nice. And there's an x in everything. So you don't actually get anything when you evaluate it at 0. So you just get something at the top limit. So we evaluate this at 2. So we're going to get 4y plus 8 plus 6y plus 2 minus nothing because the evaluation at 0 is 0. So then just gather that. That's 10y plus 10. So now the double integral has reduced to just this nice one variable integral, integrating the function of one variable, just mentioning this one. Okay. But this expression here, 10y plus 10, what that is representing geometrically is 10y plus 10 is the cross-sectional area here of this thing located at the value y, okay, in our example. Because that's the result of this inner integral. It does indeed, you see, the inner integral does indeed come out as a function of y, 10y plus 10. So that has integral, whatever it is, 5y squared plus 10y, evaluated at 1 and 3, which seems to give 60. All right. So it's 5 by 9, so it's 45 plus 30 minus 15. So 75 minus 15 is 60. Okay. So 60 cubic units. 60 cubic units is the volume. Is the volume contained between this region in the xy plane and the surface defined by that function f. Okay. So if xy is that plane there and the z-axis is coming out of the screen towards you, then our surface here is some wavy surface here in front of the area. And the volume caught between this rectangle and the surface at this end is 60 cubic units. Okay. So that's an example where the region is a nice rectangle. A rectangle that is aligned with the coordinate axis, parallel. Any questions about that example or queries? Okay, so let's look at a couple of properties and one important technique that we might use. I'll switch back to the notes for this. We just looked at that example. First one is a technique that you can use for certain nice functions. Okay. Now, functions of two variables, there's an important class of them which can be easier to treat. Those are called separable. Now, separable is a good name. You'll see it used You'll see it used around the place, importantly in differential equations. There's a notion there of separable differential equations, when one of the important functions in the differential equation can be separated out, and it makes the solution possible or easier to obtain for that differential equation. So the idea of separable is when you can separate out the dependence on x and y into two separate functions that get multiplied together to give you the original function f. Okay? So it's a particularly nice type of two-variable function, one which is really just made by multiplying two separate one-variable functions, one for the x dependence and one for the y dependence. Okay? Now, it's not true, it's special behavior. For instance, I don't think, yeah, so this function we just treated in the previous example, this function f of xy here is certainly not separable. Okay, there's no way, I better make sure that's true before I make a fool of myself. I expect that this is not separable. Probably is now that I've said that, but it doesn't look it. It doesn't. No, I don't think it's going to be. You could try and. Okay, I can't believe that one. Is this okay? So let's turn it into a question. Is this function separable? Well, maybe. Maybe reduce it slightly into this simpler question of is it a separable function where the function of x and the function of y are both nice linear polynomials? Well, of course, this would give you AC xy plus DAX plus CBY plus BD. And so if this is supposed to be 2xy plus 4x plus 3y plus 1, the only way that can be is if AC is equal to 2, DA is equal to 4, CB is equal to 3, and BD is equal to 1. And well, that's 1, 2, 3. It's 4 nonlinear equations and 4 unknowns. So, you know, I might well have a solution. So C is 2 over A. We've got DA equals 4. 2 over AB equals 3. And still BD equals 1. Although this says B is 3A over 2. So this reduces to 3A over 2. D equals 1. Now both of these seem to give D in terms of A. So we might get a contradiction out of this. This one says D is 4 over A. This one says D is, well, something different. 2 over 3A. Now 4 divided by A is probably not going to be 2/3 of A. So this is not looking good. Okay, so I don't think this one separates out. But however, when you do have separable functions, then the double integral has a nice factorization as well. The double integral factorizes into the product of the two integrals. Okay, this can be proved can be proved in a couple of steps by carefully looking at properties of the integrals. So you start on the left-hand side. Okay, so we start on the left-hand side with the integral from c to d of the integral from a to b of f of xy, but if it's separable, this is hy times a gx dx. Okay, so that's what the double integral looks like. But now, what's the idea with integrating with respect to x? When we integrate with respect to x, we're treating the variable y as if it were a constant. So this function h of y here is itself should be treated as a constant because it doesn't contain any x's. So in particular, that h of y can pass outside of the integral. Okay. So the justification for that is h of y treated as a constant, treated as a constant with respect to x, with respect to the x integral. So now this inner integral is just the integral of g with respect to x. But now inside this integral, we don't see any y's mentioned at all. It's the integral of a function defined on only the x variable, integrating it with respect to x. So this integral here in the round brackets, that makes no mention at all of the y variable. And it's sitting here inside an integral with respect to y. So this bracket here is simply, with respect to the y variable, this round bracket here should be regarded as a constant. Okay? Because it does, when you change the y variable, this round bracket doesn't change because it makes no mention at all of the y variable. So it's just a constant as far as y is concerned. So at the moment it's sitting inside here multiplying a function of y and you're integrating it. But just using the linearity of the integration operator, this can pass outside the y integral. So integral a to b, g of x dx, it's just should be treated as a constant as far as the y variable is concerned, so it can pass outside of that integral. So you're left here with the integral from c to d of h of y d1 as a separate entity. So you've got exactly the product of the two integrals. We couldn't move the inner integral outside immediately at the start because the inner integral did have a dependence on y, because there's a thing here depending on y. So you can't just pull a function of y out of an integral with respect to y. But the y can first hop outside of the x integral. Now we've got a constant with respect to y, and this can hop outside of the y integral, so that you're just looking at the simple product of the two integrals. Okay. So that's a proof of that claim about double integrating separable functions. And the last item to look at is an important evaluation technique called changing the order of integration. When you're integrating over rectangular regions, there is nothing to stop you. There's no God-given reason why x should be the inner integral and y the outer integral. We are free to change the order of integration here so that y is the inner integral and x is the outer integral. You do that just by changing the order of the differentials, dx and dy, and of course swapping the positions of the integral signs as well. Remember, a and b are the limits for x, c and d are the limits for y. So this process is called changing the order of integration. Here you're integrating with respect to x first, then y. Here we're integrating with respect to y first, then x. And this can sometimes make the evaluation easier. When we look at this example here, we're integrating the function x times the cosine of x times y with respect to x and y. Now, as it's presented there, it's presented with x as the inner integral. But if we're to follow the order laid down here, the inner integral is with respect to x. So I first have to integrate x times the cosine of x times y. Now that's a product of two functions of x, cosine of xy and x itself. Okay, it's not that difficult, but in order to integrate that, you need to use integration by parts, or just to look up the integral in a table of integrals. Okay, but the integral of x times cosine of x times y does not have an immediate simple one-step integral. It requires integration by parts. However, if you change the order of integration, so we flip the differentials and flip the integral signs, then the first integral that we have to do looks a lot easier. Because now it's a much more straightforward function of y. It's just some constant times cosine of a constant times y. It's a lot easier to integrate. And indeed, this x out here is exactly what needs to be there in order, this thing integrates to sine of x times y. When you differentiate sine of x times y, we get back to exactly that integrand there. We just integrated with respect to y, so when we evaluate this at y equals 0 and 1, the integrand reduces even simpler. Now just integrating sine of x, yada, 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 as a nice integral, minus the cosine. So changing the order here is a very nice thing to do. It makes the evaluation a lot smoother. Whereas pushing forward with the order described here on the left, okay, would require first using integration by parts. You'd have a longer. Okay, if you pushed it through, of course, it would eventually come to whatever this is, cosine of 0.2 minus cosine of 0.8. But there's a much smoother route to it here compared to the original order. Okay. So we'll leave it there for the moment. I'm seeing you again this evening at 5. We'll do a few more examples. And we'll look at some non-rectangular regions as well.